These? No, I did not visit with too many of the poisonous denizens of the Netherlands, the nether regions, but I did get to touch the spines of a platypus. Not a live one, I might add, or I might not be standing before you today. I touched the downy softness of an emu's pelt. That was pretty safe. I marveled at the wanderings of no fewer than, I think, 6 echidnas. Does anyone know what an echidna is?
Yeah, it's kind of like if a hedgehog was not as big.
Yeah, but it's a bit more than that because it's a monotreme. And what that means is it actually combines elements of mammalian type with for example, other traits of other classes of animals. So, for example, it lays eggs. Yes, the platypus lays eggs. The first platypus was. That's correct. That's correct. The milk kind of makes its way out from their skin, and I also saw the platypus, which was viewed as a hoax when it was first discovered. They sent one to England, and it was thought that the Australians were trying to pull one over on the British by showing them what they thought was kind of a crudely sewn together set of characteristics. That's exactly right. And it turns out that, under investigation, it was fine, but they originally were fooled. I also got to see some pretty neat other types of animals that live in the Australian desert, which is cool. But I also taught a course amongst all this. I had to run out. What's that? It was on use of computers for simulation modeling. And so we had people flying from all around Australia. I don't think for anyone from New Zealand this time. Last time I taught, we had some folks from New Zealand fly in as well. But about 50 people. And amongst other things, talked about the principles of software engineering that are relevant to that. So it was well attended, and I did lose my voice for some days. I was talking for many, many hours. Some of my students know what that's like. So I was talking for 8 or 9 hours and lost my voice by the end of the day. But it went very, very well, and I did get to sneak out and see the zoo. Actually, it wasn't sneaking. They urged me to see the zoo. And I saw the pandas, the only pandas in the southern hemisphere, apparently. Well, the pandas. Pandas. Like the bear pandas. Yes. They were engaged in somnolent senescence, so they were sleeping. But I got to photograph them lying around, which was good. So. I don't know where you folks, if you did anything. Yes. There's some deliverables. I hope you got a little bit of a chance to take a break too. That is important. So I'm trying to figure out. This thing has suddenly decided to present with presentation settings. Well, can we live with this? Okay, great. So let me get on my, make sure this is on. Okay, excellent. Okay, so what were we talking about before I ran to the airport? Subclassing. Okay, and why were we talking about subclassing? Good. So there's a logical progression from subclassing. Yes. So it's a primary construct of object-oriented languages, a very powerful construct of object-oriented languages, but an often misused construct of object-oriented languages. Why do I say it's misused?
Easy to little list cups.
That's exactly right. Man, you folks are good.
I mean, and also they don't even really penalize you for doing it. It's not like John will slap you on the hand saying, no, you're being a bad person. They'll let you perfectly do it.
That is exactly right. And in that sense, it's like, well, yes. So in general, with the list-scope substitution principle, we have this issue that most violations of the list-scope substitution principle go unnoticed until people run into a bug, so they run into a defect, or until a peer review discovers it. There are some violations of the list-scope substitution principle that a compiler, a build, will catch. Give me an example that it will catch. Yes. So specifically with respect to, for example, parameters, return values, and exceptions associated with subclasses, there's this whole issue of contravariance and covariance, whereby the if B is a subtype of A, then the return types of B can be what of those of A, of the corresponding method in A. They can be subtypes of the corresponding method in A, or the same as. And the parameter values can only be supertypes of the corresponding method in A. A little bit confusing there, but it's a generalization of the principles of the list-scope substitution, or an extension of those to typing. And compilers can discover that. And there are languages which will allow you to apply those principles and will discover violations of contravariance and covariance. They allow you to have subtypes where you have a corresponding overridden method, but where that method's signatures don't have to be exactly the same as in the supertype, right? And so compilers will be helpful there, but they won't be helpful for discovering violations of the list-scope substitution principle in terms of preconditions, postconditions, invariance, history properties. In general, they won't help with that. Why not? Why can't they help with that? Well, there's this awkward little thing called the halting theorem.
Basically, there's no possible way to figure out whether a program will stop or keep going on it.
That's correct. And an extension of that is you can't prove automatically that, in general, that one method performs actions that are incompatible with another method. You could make it, you could cleverly construct it, so the only way you could know that is if you could figure out if this certain thing halted. And that's not going to be possible. So compilers, ladies and gentlemen, have limitations about what they can do for us. Now, all of us have encountered those situations where a compiler is being fussy. It's preventing us from compiling some code that we want to compile, that we know is correct. You struggle with it, and it's complaining about this or that or this other thing. One of the reasons you should be sympathetic to a compiler there is it's trying to err on the side of correctness. Sometimes it's trying to be a bit more restrictive to be sure that it's correct. And in general, compilers have real limits on what they can automatically deduce. And so they tend to err on the side of saying, okay, I'm going to be extra restrictive, prevent you from making a mistake here. Why is it in our interest for compilers to be a bit picky?
Makes us think a bit harder about what we're doing with
That's true. And it's better that the compiler is picky than what happens. Yeah, and who does it happen in front of? Your client. It happens in front of your client, folks. That's who it happens in front of. I don't know why, but there's a Murphy's Law that applies to computing, and if you got your bug in there, it's going to be found by a user often, very often. So the point is that it's better a compiler stops us from making certain types of mistakes than there's a horrible bug which emerges in front of a client. And so often compilers are a bit extra restrictive, but fortunately, if we really know our craft as a software engineer as well, we can work around those restrictions, even if it's not always in the way that we want to. So today, we're going to revisit the issues having to do with the Liskov substitution principles associated with classes and safe subclassing, because I want you to be clear on that. But we're going to be going on quickly to this issue of skeletal implementations and mixins. Mixins. Now, one of the teams here is admirably using Scala as its main language for development. And in Scala, there's a special support for mixins compared to in other languages. We're going to see how we can support them via skeletal implementations, this technique here in Java. But we'll also see how traits can be used to provide for mixin functionality within the context of Scala in particular. Now, tell me, I know there's been plans shifting on this. In 340, are they covering Scala right now?
They're covering
Haskell, okay. Okay, so how many people here have encountered mixins before, using mixins? Okay, I was thinking it might be some folks from 340, but it sounds like not. So we'll talk about it a little bit more as a context. Okay, so tell me with subclassing, in terms of review, what gives with subclassing beyond the Liskov substitution principle? After all, if we declare one class a subclass of another, if we declare B a subclass of A, we need to ensure the Liskov substitution principle applies for B, so that in some sense it's compatible with, it's consistent with the promises given by A, right? That's what the Liskov substitution principle is about. It's about the promises made by class, by subtypes compared to the promises made by the supertypes. Because we may think it is an instance of the supertype when we're manipulating it, and we need to be able to count on the guarantees that are applied to A. So what else is new in subclassing? Why are we spending 2 lectures on subclassing as an issue? Issues of overriding methods. Yes. So overriding is an instance, a specific component. It's a big component. It's probably the most important component of these issues that come in with classing, with subclassing. What are, in general, can we generalize that a little bit from inheritance of methods? It's inheritance of what? Functionality and begins with an I, ends with an N. Implementation. This is no longer a matter of merely adhering to promises like the Liskov substitution principle. This whole thing about walking into FredX and finding that they require packages by 9 a.m. and it being a violation of FedEx's properties. This is now an issue of implementation. How does FredEx actually get that package to market? And the deal is, if it reuses, if the implementation of B reuses elements of the implementation of A, you need to know more about A than you would if you were merely using instances of A. If you're merely making use of A's. You need to know more than what A promises to people who use its instances. Certainly B has to adhere to all those promises as part of the Liskov substitution principle. If you use an instance of B, it has to adhere to the promises made by instances of A. But with subclassing, if you're going to implement a B in a way that uses the implementation of A, you've got to know about some of the internal details of A. When I say internal details, can you give me some examples of internal details? Okay. Sometimes that can be the case, but in general, we're trying to achieve subclassing in a way that's somewhat modular. So hopefully we'll be able to hide some of the information about how A works. But there are certain types of information that we routinely will need to know about the implementation of A if we're going to implement B, depending on that implementation. depending on how A works. If we inherit A's methods, but also its instance variables and those sort of pieces. So bubble sort, quicksort, sort of how the algorithm works to a degree. What key things that we talked about last time before I ran off, what key things are at issue? It's often what calls what. Do you remember that?
It's how the different methods call each other.
How the different methods call each other
Within the class.
within the class. Why is that?
There could be unintended side effects that you wouldn't be aware of if you're just using an instance of the class. Like we had that
Yeah.
example where we had that timer and it didn't count properly because we didn't know that one function in the super
Yeah. Exactly. Exactly. So here we're dealing with the province of implementation issues, and generally here we're dealing with a subclass that's overriding some methods and using submethods directly from the superclass. Some of the methods come directly down from the superclass; they aren't modified, but some are overridden. Right? Remember that? Now, suppose we use a method directly from the superclass. Does that mean that that method will behave exactly as it does in the superclass? So we suck in all this implementation of the method in the superclass. Will it behave the same? Why not? Why might it not?
It's using other functions.
That is the issue. That is the issue. Remind me your name. Andrew. So Andrew exactly hit it on the head. So if we have this method, foo, in the superclass, and we have this class B that extends that superclass, and it doesn't override foo. It just reuses foo. Right? Does foo behave in the exact same way in B is the question. And as Andrew pointed out, the answer is not necessarily. And in this case, foo calls off to, you guessed it, bar. And here we've overridden bar. So suddenly we've changed the functionality of foo without overriding it explicitly. We could look here. Where's the override of foo? There's no override of foo, but we've changed its behavior. Have we not? We've changed its behavior. It's calling off. It thinks it's calling off here to bar. But it's actually calling off to our bar. So we have actually changed exactly what foo does. And for the example we saw, to which Warren referred, that can lead us to kind of make this mistake. And we had a nice example. Oh, man. Oh, I guess I cut it out. Oh, great. And abbreviating some of this stuff. But we had this example. Remember where we had add all and add? And the question is, does add all call add or not? If add all calls add, and we override add to keep track of the number of times things have been inserted, then we don't need to override add all, because it's already counting these things by calling off to add. On the other hand, if add all does not call add, then we need to override it so we can add that mechanism, right? Remember that? And what's worse is that it's not a matter of option of overriding it. We need to override it because having it call, otherwise it won't count these things. And so it may be a matter of correctness. Now, again, I argued last time in the hurried minutes before my flight, it was a tight one, I argued that it's not merely a matter of being able to go look at what A does. Suppose A is totally visible to us. This is an open source project, and we can go look at the code of A. And so we say, oh, add all does call add. So we'll just override add, and does that make it a fine decision? Is that the end of the game?
No.
Why not?
Easily change it in a patch 6 months.
They can change it in a patch 6 months down the road, and then we're hosed. Then our code is going to break. Our code is going to break because they changed something, And they didn't know anything about that our code is circulating, and suddenly our customers are complaining, which is not a good thing. I know, because I've had them call me before. I don't mean your customers. Okay, so I argued here that basically in the franchise example, this is like FedEx making use of the internal mechanisms of FedEx, shipping it via FedEx's planes, and they sure as heck got to know more things, like FedEx's plane schedule if they're doing that. So I talked about several ways of dealing with this subclass issue beyond the Liskov substitution principle. All of these things about the Liskov substitution principle are still at hand. We need to be careful about adhering to that, but we need to deal with things elsewhere. And I argued that one way to do it is to simply say, hey, I'm not going to allow my class to be subclassed. This class is a final class, and you're not going to be able to subclass it. And that means we don't have to worry about providing lots of information carefully to the folks who use our class, who are using our class. We don't have to worry that they're going to subclass it. And Java, amongst other languages, provides a very nice way of doing this with a final declaration. So that's good. Now, it turns out that we looked at another way as well, though I didn't emphasize it that much, which is this notion of a composition and wrapper class. And I want to hit that one more, because I feel I didn't do it justice last time. But then I provided a bunch of different ways that you could provide, or two major different ways that you could provide safety in subclassing if you want to allow it. And these ways we're providing interfaces that are geared towards not users of instances of A, for example, but instead are geared towards people who are going to subclass A. So suppose I want to use an instance of A. So here I have some code somewhere else in my system. It's in a method called Baz somewhere, and it takes some things. Maybe it takes in an A. Yeah, it takes in an A. Here we go. And I'm going to call off to various things in A such and such. Okay. Do I need, if I'm using an instance of A, what might be an instance secretly of B, do I need to know anything about what method calls what method in A? If I call add all, do I need to know that it calls add? If I'm just using an instance of it? No, I don't need to know that at all. Why do I care? As long as it does its job as indicated by its preconditions and postconditions, as long as it does what it promises, I don't need to know about all the details of how it does it. True or not? So that's true. But if I'm going to create a subclass of A, this guy here, I will, in general, need to know this extra information. So I had this notion of a subclassing interface. And once again, we have that balance. We don't want to promise too much. We don't want to promise too little in this subclassing interface. What's the problem with looking at the Liskov substitution principle, for example? What's the problem with promising too much? In other words, being too voluminous in what we promise.
You might hem yourself into what you expect.
That's exactly it. Man, that's excellent, Warren. We hem ourselves in. So we basically restrict our flexibility in evolving the implementation of A. Now, that's something that doesn't come out on the shoulders of our users directly in the sense that their code suddenly breaks, but it does limit our ability to engage in performance optimization of A in a way that might benefit our users, right? It might restrict us from changing some aspects of the implementation in a way that's needed for certain use cases that would make them very efficient. So, if we promise too much, we're limiting this. If we promise too little, what's going to be the problem? Suppose we don't have any specifications at all associated with A. What's the risk there? I love it. It's a Greek chorus. I asked them to speak as if a Greek chorus in Australia, too. And they did. I might note they all intoned in that special accent in a Greek way. They knew what I meant, amazingly. So why? What happens if you promise too little? What happens if you don't say anything about what you promise?
You have the same problem that you started with.
Yeah. Yeah. People don't know what to count on, and so they do one of two things, right? What do?
They start making assumptions.
They start making assumptions, which could be fragile. Oh, it seems like this takes a null value. So I'm going to call it with null values. It doesn't say whether it does or not, but it seems it's okay with it. Could break in the future. Yeah.
And then they update and the load comes crashing down.
Yeah, that's right. That's right. So there they get, their code breaks, and you don't realize they're counting on this thing. Windows had big problems with this. In fact, I think it still does, because there were a lot of things that were undocumented about it. And so people would say, well, seems pretty good. I think this will work. And Microsoft, because of that, doesn't know what people are counting on. And so they're counting on all sorts of wacko things about the Windows API, to the point that when they had to re-implement the API or create new revisions, they had to make it bug compatible. Right? They had to actually recreate the bugs in it. And Mono was doing a similar thing on the side of recreating .NET. They're making it bug compatible so that they reproduce the bugs because they don't know if people are maybe counting on these bugs. So that's a sign that you're promising too little. Another thing that people do is they avoid using your class. So you lose customers. They go to someone else whose API is better, who's more clearly documented. I mean, it's a very real thing. People like having some clear understanding of what is supported, and poor API documentation is a reason that people might shy away from your product. So it's a very real issue with respect to documentation. So it is with subclassing. If you're not providing implementation of what calls what, you're putting your subclassing potential clients at risk. People who want a subclass but don't know what they can count on. It's a risk. Okay. So I showed last time, again, in a very hurried way, this issue of providing extra information that's associated with a class. And for example, it notes that this instance is called by an iterator's remove method, the iterator associated with this, or what things call remove range, for example, here. It notes that this thing is calling off to list iterator.remove here, etc. So you're providing some additional information. And that's the main thing I wanted you to know about. You can provide some information about what calls what so that people have this understanding that if they override bar, they are changing the functionality of foo as well. All right. Okay, and they know that they can count on that from now on. It's not about what is there now, it's what they can count on. It's what's guaranteed as part of the contract. I talked about avoiding self-use of overridable functionality, this idea of where here, rather than having this issue earlier, we instead have something like this. So we have this bar internal, and instead of foo calling bar, foo calls bar internal. What's the advantage there? It's that bar internal is only exposed internally. It's not actually, cannot be overridden. It's private to this method, and I should really have that be clear here. So if you override bar here, you've overridden the bar functionality, but you have not changed foo out from under it. Does that make sense? You haven't changed how foo behaves as a side effect of overriding bar inadvertently as a side effect of overriding bar. Instead, you've just changed bar, which is perhaps much closer to your intention. Of course, if you want to override foo, could you do so? Yeah, you just override it. But the point is, it's modular. It's what? It's explicit. It's orthogonal. You know, one thing is at a right angle to the other. You go this way, or you can go that way, or you can go some combination of them. But by heading one way, you're not automatically, you know, overriding foo by or changing its functionality by accident. So it's explicit, clear cut as to how this inheritance works, which is helpful. In general, it's really nice to have clear-cut things, particularly when you're tired, jet-lagged, and you're working late at night. I can speak to that with confidence. Great. So, you know what? Another issue, though, that I wanted to get back to was this issue of inheritance versus composition. And I argued this is part of the discussion of avoiding overriding. And, you know, I noted that composition, this idea of, it's also sometimes called aggregation, or where you have, in wrapper classes, it's an instance of it. Here, we have reuse of code, but we do so in a way that isn't just merely using overriding. So, for example, we have a hash set here that supports add and add all. And here we have, you know, this implemented hash set. This is this example with add and add all that's instrumented. And there's the question is it safe or not? And an alternative to this is you have a wrapper class. And I had the uncomfortable feeling that I might have been rushing this discussion last time, so I want to be sure that we're clear about it. The idea here is that we have some set, which could be, you know, any number of implementations of set. And we want to create this instrumented set here, which has this add all and add. And the key difference is here that instead of, well, this implements the set interface, the actual implementation that it uses is internal. It's a set S. That's actually an instance of some implementation of the set interface, right? So we have an S here, which refers to some reference to something that implements set interface. Now, having done that, we're not overriding add and add all as methods here. There's nothing to override. It just implements set. It doesn't actually use an implementation of set. It doesn't extend an implementation of set. Instead, we have a add and we have add all, and they just implement this functionality here. They don't override anything. And what do? How do they work? They call directly to whatever this refers to, whatever implementation of set it refers to. They call off to it. Now, suppose we implement add like this. So we implement add in this sort of way. Have we changed the functionality of, or even better example, suppose we've here override add all. Have we changed the functionality when we call s.add all? Have we changed it because we've already overridden add? Do we have to be worried about that? No. If we call s.add all, could it be calling our add? Why not? It's not part of the class. We haven't overridden anything about how S works. We haven't changed how S works. So whether S's add all calls its own add or not doesn't really matter to us. It's immaterial. We haven't changed inadvertently how it works. Does that make sense? We haven't changed how S's add all works at all. Why not? It's because we haven't overridden. There's no chance we will have overridden its add. Whether it calls off to its internal add or not is its own business. As long as it does its job, we know that it's doing its work there. At the same time, we're keeping track of this extra information here on this. Have we made use of S's functionality, or if we had to re-implement it from scratch? We've made use of it. We call off to add all, does its work. Call off to its add here. We've made use of it. It's not like there's no reuse going on. The difference is that it is safe reuse. Safe reuse. It's reuse where we don't have to worry about how S works internally. We just call F to it. And Kurt, I'll be with you in just a sec. What's the primary disadvantage of this? Looking at this. Yeah, it's all these forwarding methods. We have all this kind of cruft here, right? Where our clear calls off to S clear, contains calls off to its contains. But in the grand scheme of things, I'd rather live with this than with bugs. Several issues that I need to fix because I've accidentally overridden this, and some code somewhere is counting on this feature which I broke by accident because I didn't know that internally this implementation of SAT, one method called another. This is pretty straightforward stuff. I mean, especially given that it's labeled here as forwarding methods, you kind of look at it and say, okay, I don't need to worry about that. Yeah, it's stuff. It's stuff that clutters things up, but it's got a clear function. And as long as I'm really consistent in calling off to the appropriate one, it's pretty straightforward. And I argued that in coming years, probably this will become more and more automatic with languages supporting it. But Kurt, you had a question.
Well, you answered one of them, but I think there's two more.
Okay, good.
So instead of doing any inheritance, you could always do this and never sort of like full on inherit it, because anytime you might want to override a method in the future, you might as well just have it done this way. The only disadvantage is those forwarding methods on the bottom.
So, yes, could you do it that way? You absolutely could. Could you have a language that forbade inheritance, forbade subclassing, and only provided for this sort of composition? Yes. Are there such languages? Yes, that have chosen to do that. There's a sense that it's good to provide the option of subclassing, but this is always the safe fallback, and it's not too bad.
Yeah, it's just the methods on the bottom. But you could easily conceive of something that would automatically do those.
Yes,
Forwarding methods.
indeed. And we're going to be talking about Mixins in skeletal implementations in a way that provide the clarity of this approach, but but avoid a lot of this cruft down here at the bottom. We'll be seeing those in the coming minutes here. Okay, but the other question.
My other question was, if you had inherited it and then you wanted to change it up,
Change it up.
you wanted to switch it to this implementation.
Yeah.
Let's say you inherited a method, you didn't override anything because it was fine the way it is, but then in some version down the road, turns out you want to do some overriding, and in order to protect yourself, you want to do an implementation.
Yeah.
Now you have to change all of the functions that depend upon S. Is that right?
This is correct, but you would, more to the point would be, and this is an issue for you folks in your implementations, if your code previously, maybe you had B subclassing A here, right? If you had this, and now suddenly you want to make B use a wrapper class of A, now you've got this awkward situation is where people are counting on the polymorphism of B. They're counting to be able to pass it around as an A, and you're not going to be able to do that anymore. So instead, what's a safer bet, and this is a good principle in general, is if A has an interface associated with it, I sub A, rather than, it would be desirable if people, when they're thinking about using B as an instance of A, just treat it as an I sub A, because then what you could do is you could change it to be this, where internally you call off to A as a wrapper class. You use A, but it implements I sub A, and this is all they're counting on. So you're fine. But if they're counting on being able to pass around as an A itself, as a full implementation of A, then you've got problems, because now it's no longer an A. Does that make sense? Yeah. Well, I mean, you could. It would just be having an extra. It would kill a lot of the benefits unless you had an extra, reference to an extra one of the A's internally. So you inherited from it, and then you have an extra one internally, lowercase a, that you just call off to in a wrapper, in which case you've gotten double it's kind of a perverse thing, where you're throwing away the benefits of subclassing, and you're having extra mechanism there to get you wrapping, and so it gets awkward. But if people are counting on this only being an I sub A, instead of counting, and this is good practice in general, rather than referring directly, hard coding that this is an A, a class, you refer instead to the interfaces by which that you need for this class. Wherever you use instance of A, instead you write I sub A's. And then if someone later wants to change this class from being a subclass of A to just implementing I sub A, they can do that and pass around to B as an I sub A. It's fine. So you can do that. And there are good code bases. I've seen top coders do exactly this. They don't actually talk about passing around a concrete class, an instance of a concrete class. They're typically dealing with instances of interfaces that happen to be implemented by this class, because that's all they need. They don't need to know it's an A. They just need to know it's this interface implemented by A. Does that make sense? Huh? So that's a good practice to decouple these things, because it decouples these classes and lets you change how you're going to implement B here more flexibly than if you're counting on it being a subclass of A. Because really what you may be counting on is that it's an implementation of I sub A. And whether it does so via wrapping or does so via subclassing, folks who use B don't need to know, right? To give flexibility, all they need to know is that it implements I sub A. Does that make sense? These are some of the subtleties I didn't have time to go into last time.
But if you have everything implemented in the interface instead of actual things, wouldn't the fact that they're all implementing interface provide problems for people to expand?
Well, okay. Be clear, though. Maybe it was just a choice of words there. When you say implemented in the interface, do you mean declared in the interface? Because remember, the interface doesn't, in general, have any implementation in it.
Yeah, that's what I was saying. Like, if you want to add more function parts to the
Yeah.
interface, wouldn't that be extremely hard to do?
It's a good point. So in general, we're very hesitant about changing interfaces because these are viewed more clearly as contracts. And changing interfaces is viewed as a heavyweight thing. But so, frankly, should changing the contract associated with A, going and implementing methods or changing methods. If you have code, lots of code elsewhere in your system, in C, D, E, F, which are all counting on this and how it's implemented, then if you're changing the contract here, you may break a lot of this code base as well. So there's that same issue whether it's in an interface or here. Interfaces in Java 8, by the way, can have some implementation in them. In a very restrictive way, but that would be a different lecture. But they can have some mechanisms in it. Any other questions though about this issue? Okay, so let's talk about. So there's these wrapper classes, and you'll notice in this wrapper class here, it actually does undertake a similar thing, an implement set, which is the interface associated with this. Just implements that. And whether it does it via subclassing of something or just implementing and redeclaring all these methods, the folks who use it shouldn't have to care. And this is one of the reasons why when we use a class, preferentially referring instead to that class directly, we refer to the relevant interface that we're making use of. That's a safer type of reuse. So here we're implementing this class. Okay. Right. So I think I'm going to right. Okay. So this is this internal use, and I want to get onto these wrapper classes here. Okay, sorry, into these skeletal implementations. Okay, so let's talk about this notion of skeletal implementation. This is a scheme that provides most of the advantages of inheritance without loss of flexibility. And it uses interfaces to describe functionality. The basic idea is for each interface, you provide an abstract class. So if you have an interface I sub A, you have an abstract class associated with that implements the interface. And the key thing about this skeletal class is that it leaves certain methods unspecified. It does not provide implementations of them. Just as a reminder, folks, what's the difference between an abstract class and a full class?
An abstract class can have stub functions that aren't fully implemented.
Good. So an abstract class in general is not going to be able to be instantiated because it's incomplete. It hasn't provided implementation of typically key components. And so it is here. There's an abstract class that doesn't implement certain key elements of the interface, but does fill in a lot of other stuff. So there's kind of these primitive methods often, these kind of most basic methods that are left unspecified. They're left to be determined by someone who subclasses this abstract class. And Java has many of these classes, and they're typically called abstract interface name. The abstract indicates it's not a full implementation. It's a partial implementation. And therefore, you can't say new abstract, in this you can't say new the name of the class because it's incomplete. It's an abstract class. It's not a full class. So if you want to use this thing, then what you do is you implement the interface. You implement this guy. You say implements this guy. So you want to create a class. I guess we're up to G. It's going to implement A here, I sub A rather, and then it will often extend the abstract version. So it will extend. In other words, it will inherit from abstract I sub A, which itself implements this. So this one isn't even really required explicitly because it's implied through subclassing this, that it implements I sub A as well. It's provided automatically through this subclassing. Here, you can inherit from the skeletal implementation that's shown here. Alternatively, you can create a wrapper class that uses this, an anonymous subclass of the skeletal implementation internally. So here we would have an H that internally makes use of an abstract, a subclass of abstract I sub A. This would be a sort of a subclass of it, which is in itself, it implements this, this interface here. So let's take a look at what this looks like. So here's an example of skeletal implementation. So what, if we look at this, based on what I've just said, what is it that distinguishes this as being a skeletal implementation?
Well, some of these things aren't finished, like, for example, that.
Yeah.
Is that pub 1? What is the first?
Would you turn off the front light?
Yeah, it's kind of hard to see that.
Yeah. Could someone get those lights? That's great. Thanks, Alan. Much appreciated.
There it is.
There we go.
Value only has the fact that throws an exception, for example.
So say this.
The set value function, yeah, all we know is that throws an exception.
Set value. Oh yeah, this one here. Yeah. This actually, yeah. So this just throws an exception. So here we actually implement it, but basically we're implementing in a way that will cause a problem. Okay. And you'll notice that get key and get value are not implemented at all. Right? So we're saying this implements map.entry, but then we're not providing implementations of those methods. But we are providing implementations that are meaningful of several other methods, like hash code, equals, equa, and equals. So here we are providing some mechanisms, but we're leaving others that are not filled in. Now, having done this, how would this be used then? So we've filled in many of the methods, but we've left some to be filled in. So what do we have to do in order to use a class like this? You have to fill in those methods. And so I'm trusting that you folks have seen this before, this sort of use of Java constructs, where you say new, for example, abstract list, and you have these brackets around. What's going on here? I don't know that everyone will have seen this before, so it's important to be clear about what's going on. You're saying new abstract list. Now, this almost seems like a violation of what I told you earlier. The definition of abstract classes, you can't just instantiate it. You can't say new this thing. But what else is happening? What's the stuff between the brackets? You're defining the things that are missing. So you're saying, okay, create an instance of new abstract list actually, it's a subclass, an anonymous subclass of this. So you're actually not creating an instance of abstract list. You're creating an instance of an anonymous, unnamed subclass of abstract list that has all the implementation of abstract list, but then these extra methods that are overridden here, which weren't provided in abstract list. So size, get, set. Those things were not provided as part of abstract list. Because they're provided here, we can say new of this thing because it's new of a complete class. We've got most of the stuff from abstract list, and we filled in these extra components. And we now return this as a list. Guess what this is? This is a class list? It's an interface. It's an interface implemented by, guess what? Abstract list. So abstract list is the skeletal class associated with list. It fills in a lot of great stuff, but it leaves certain methods unspecified. And if we want to make use of an instance of it, we can fill in the rest and return it as a list, as its associated interface. And from then on, it can just be treated as an instance of list. It happened to be based on a class that has no name directly. It's this anonymous subclass of abstract list, but that's okay. It has this get method, this set method, this set, this size, and this get, which is fine. So here, folks, we actually have this anonymous class that it provides these mechanisms and that implements this interface here. And we've done so in a way that has used the benefits of subclassing, but without exposure. We haven't actually overridden methods that are already defined in the superclass. We've just filled in methods that were missing. Notice one important thing here, folks, and this is a very useful thing, particularly in light of Java 8's use of lambda expressions. This kind of presages it. You notice that this int array as list, it passes in an int array here, right? And you'll notice this abstract class here, this concrete anonymous class, it actually refers to I sub a. See that? It's actually referring to this thing that we passed in. It's captured it. It actually remembers this I sub a here, and it can actually make use of it. This is a very nice thing. It's because this is a final. It's a final parameter here that it doesn't change, and as a result, we can just within this here we can actually make use of those mechanisms. It's almost as if it's a field of this anonymous class that's being returned. It remembers this reference here. So we can actually remember it here. So this is a useful method. We're not actually overriding things in a big way. We're actually making use of the functionality provided by abstract list and providing some additional components. Here's another example. So we can declare some X list that extends abstract list, and it provides get, size, and set, and these are just filled in because they're not defined in abstract list. It's the same basic pattern we've seen in the last example here. Here it was an anonymous class. We said new abstract list, and we filled in the methods, and this is basically some anonymous class that's a subclass of abstract list. Here we actually have a non-anonymous class. It's actually explicitly a subclass of abstract list that fills in these methods. So this is an example of sort of safer subclassing in the sense that we're not changing methods of abstract list. Rather, we're just filling them in. We're filling in these methods, and by implication, we're implementing some interface, in this case, list. Okay, so here's a little use of a skeletal implementation. Here we have a situation where we have an X list. It implements list, and it extends some other class. This is important because in general, in Java, we can't have multiple inheritance. We can't implement abstract list and implement, we can't extend Y and extend abstract list. So instead what we can do is we can have a delegate that we define here called list delegate. And this is a list. Somehow the formatting of this got screwed up. And this is based on an anonymous subclass of abstract list, which is great. And then we can simply delegate to this instance. So we could delegate things like size and just return list delegate.size, for example. So here we get many of the benefits of dual subclassing, of multiple inheritance, by simply implementing a sort of wrapper of sorts. But here we are not needing to do quite as much work as we have to if we built it up from scratch. Instead, we use this this anonymous subtype or anonymous subclass of abstract list, and we can simply delegate to this in this fashion. So we can extend Y, and we can essentially benefit from an existing implementation of list in the form of this anonymous subclass of abstract list. Are people comfortable with this notion of a skeletal class? This sort of notion, where you have this is a skeletal class here. It's filled in a lot of pieces, and you're just filling in the remainder. Are people comfortable with that idea? Yeah.
But that only makes it significant if you are inheriting the simple. I mean, if you're wanting to override the simple function, or like the ones that have.
Right. Right. And that's generally how these are defined. These abstract classes defined. So they take care of many of the other methods which depend on the simple method, the primitive methods. And then you just fill in the key primitive methods, and you're done. Because often we'll have in a class, we talk about classes. They used to talk about this in 270. Do they still talk about how if you have class A and class B, they should exhibit, so here's a class B, they should exhibit high internal cohesion and low coupling between them. So you don't get A using B that much. Maybe it calls off a little bit, but there's a lot of internal sort of use of A here in the sense that a lot of A's internal mechanisms call off to itself. Is that recognizable? Okay. So in general, Kurt, if we have a class A, a lot of its methods will be calling internal components. And And often there's a few key ones, get, set, size, whatever, like here. And this is kind of reserving those for implementation by folks underneath and providing the implementation of the rest of the stuff which depends on them. And so here, these don't have to be overridden because they were never defined in the first place. By the same token, you don't have to be worried that by overriding one of them, you are accidentally, going to change the behavior internally of a whole set of functionality, because these are designed to be overridden. Does that make sense?
Yeah.
Yeah. Sorry? They're designed to be implemented, that's right. If one of these, for example, was already there and was calling off to another one of these, if get had been implemented, was calling off to another one of these, then you might have to worry more because you might override this one, but you've accidentally changed the functionality of that. But because these are designed explicitly to be implemented by an end user, they are used in the class in a way that that recognizes that, and there's knowledge that you have to implement all of them together. So you have to put them all implementations in place. Does that make sense?
Yeah, thank you.
Yeah. Okay. So this is a notion of sort of an abstract class that implements most of the functionality. So this is called a skeletal implementation. And it's explicitly used with interfaces, with an associated interface. Does that make sense to people? Okay. Let's talk about mixins now in the final moments of this class. So mixins are a technique which go back many years. I believe it's the Common List Object System, CLOS, which goes back decades. And the basic deal provided by mixins is a decoupling of the benefits of subclassing and subtyping. Okay? So, subtyping. So, here's a question, folks. Can we use subtyping in the absence of subclassing? You bet we can. We can have an interface, and we can have a class that implements that interface, and we've gotten subtyping. We can pass the class, instances of the class around as if it's an instance of that adheres to that interface, because it is, and we can get subclassing or subtyping because of that. It's very good. We can have another interface, I sub B, that depends on I sub A, right? True or not? True. Okay. So we can get this by itself. Normally, subclassing depends on subtyping, right? You normally declare a subclass. One class is a subclass of another. B is a subclass of A. And it ends up automatically needing to adhere to the list-scope substitution principle because now B is a subtype of A. But with mixins, we're separating the benefits of each. So with a mixin, you get inheritance without subtyping. We can reuse implementations without implying